Are some people choosing not to be part of the recording or something?
This call now being recorded.
Maybe they're opting out, so they're jumping off. So we're back to here. I wanted to get a few questions in iceberg. So in university physics. Let me just find it from the table of contents. And some people are allergic to. And the index. Uncertainty principle is 36, 37. So I see there in 38 because they're saying revisited. Yes, so 1265. 12. Why? Why doesn't this thing go to the exact page? So a lot of these uncertainty equations are determining the maximum and minimum. So if we have maximum certainty in one quantity, that means, and we're multiplying two of them, that means for the other one, the uncertainty becomes at a minimum. So in that case, we're seeing the minimum amount of time. What else? Yeah, sometimes also we take the order of the uncertainty to be to the same order as the measurement in some of the cases. So for some people, if you don't multiply through by the electron volt, by 1 electron volt, still you're halfway correct if you state that the order of the error is to the same magnitude as the measurement. We usually do that for larger quantities though, so but you have to state it. Let's see if we can get an example. It's just showing the intensity and then the probability of this wave. So this is the same thing that you have. And then the darker bits, of course, have a higher probability of particles being there. So the Max-Born interpretation is almost like a reverse of that. The explanation to the double slit experiment, you can also check iceberg, not iceberg. That book is called Iceberg. So today this thing is not showing up as black. So those are the bits which are defined the uncertainty in the x coordinate. So the uncertainty can be uncertainty for all the coordinates. Delta x, delta y, delta z, or delta v, which will be a volume, but usually we are looking at one dimension, but it also works. So in this bit you see by the uncertainty is given by h bar over 2. They have the reasons for that as well. It would be the boundaries of their wave packets, but couple of things it could be, but I already mentioned it that sometimes you have h bar over 2, h, so it's not really a sticking point. So this is a restatement of the it's impossible to determine both the position and momentum of a particle simultaneously with arbitrary great precision or with to the same degree of preciseness as classical physics would predict. So this Heisenberg is different from what we had as allowed energies. You might be tempted to go back there, but this is just a fundamental limit of how accurately you can measure stuff. So I know time is measured in 1 part to the billion. So again, we have just reiterated there's nothing special about the x-axis. You can have that bit. Yeah, so the uncertainty in one component is not related to uncertainty in another component. So you can have delta x, and then delta px, and then delta y, and then delta py. So though so there's a question there, an example. If you could trap a butterfly in a net, let's say you guys who try and hit mosquitoes or trap stuff. So if you're not able to trap it, is it as a result of the uncertainty principle? Because if you're going to slap something, you need to know where it is precisely. If you're going to trap a butterfly, you need to know where it is. Now, suppose you have a net of 0.25 meters, that is 25 centimeters. And then that means that the uncertainty in the butterfly's position is approximately the dimension of your nets. That's what I was talking about, where I said that sometimes the uncertainty is to the same degree as the what? As the measurement. So delta P, the uncertainty in momentum, which you need to know, would be about 2.1 kilogram meters per second. There's a big assumption here that h bar is 1.05. So if the butterfly has a typical mass of, if h was big, you'd have your delta P as 2.1, the uncertainty in momentum as 0.1 kilogram meters per second. So if you add your butterfly, so P is equal to mv, that means uncertainty in velocity would be about 7,000 meters per second, which is the speed of sound, or a baseball traveling at 300 meters per second, which is the speed of sound. So that would be too much kinetic energy that you use. Of course, Planck's constant is much smaller, so h is going to be to the order of -34. So the uncertainty in velocity, you can calculate the actual uncertainty in velocity by the uncertainty in momentum, which will be to the power -34. So if you divide that by 10 to the power -4, you get uncertainty in velocity, which is very small. So even to the width, even if you're using a bigger net, the uncertainty in smaller nets, the uncertainty in velocity is very small compared to what you'd need. So And that uncertainty is dictated by the size of Planck's constant. There you have those graphs which we looked at and how to add them together, and then that uncertainty in energy. So there are more examples in there which you should look at. There's some from the past papers which you should discuss, and we can't look at all of them here. So our time is up, or nearly up. Actually, it's up. I thought we'd end by 10:45. I have a meeting at 11, so I'll just wrap up with the teaser to the Schrodinger equation. So what will that teaser look like? We'll have to come back to this PDF. Yeah, so this teaser here is, of course, we spent considerable time explaining the wave function is, and we saw that the wave velocity is equal to the phase velocity, which is also equal to the velocity of the particle within that one that is in this PDF. So the teaser is as follows. So we're going to assume a wave group, and that wave group has a particle in it, and we have already seen that the particle the probability of finding the particle is proportional to the amplitude, and so we know that that wave packet contains a. Now the total energy of this wave group is given by the sum of the potential energy plus the sum of the kinetic energy. Now kinetic energy you can easily get from the angular velocity, and then or the frequency. So the frequency gives you the angular velocity, which can give you k, and it can also give you momentum. So the potential energy is given by p squared over 2m, and the x so the p squared over 2m is okay. It is kinetic energy, right? Because that p squared over 2m is, if you convert it back, it's half mv squared. P is mv, so that expression should give you ke, which is half mv squared. So that's your t, which is different from T. Amale, who is a comedian. So that's your T. And then V is a potential, or potential energy. Now, we won't look at potential energy later on, but at some point when V is equal to the square root of what? Twice ME twice M, I think E, where E is energy, and sometimes is just given as the EV. So that V is significant, and also is that potential. So next time we'll be looking at, okay, maybe before we say next time, E is equal to HF, which is, so all these are different expressions of energy. This is KE, and then H omega is just the energy which you get from Einstein, not from Einstein, from Planck. E is equal to HF, and then P squared over 2m is the kinetic energy, then Vx is just the potential energy. So you remember we had our wave function, and so then we find dt and then end up with omega. So we have our defined dx, and then the second derivative of phi with respect to x, and also the second derivative of phi with respect to x for so with phi with respect to like y for another variable. But in this case, we want to get defined dx and defined dt. So and there's a very good reason why. So we substitute from our definition of the Schrodinger function, and we end up with this. So yeah, that's what we end up with. And so next time when we're able to meet, which I'm not very sure, tomorrow is quite busy, so we're not meeting tomorrow. It's busy till like 4. So I'll see when we can meet, either early on Wednesday or another time which is a bit more flexible. We'll discuss the class reps. So we'll continue there, and we'll see how to derive this Schrodinger equation. But one disclaimer for 30 seconds, you'll see we don't, so it's not a derivation to the Schrodinger equation, and Schrodinger just came up with this equation either by a dream or by something, but it just was able to explain motion of the electron as a wave very, very well. And it's able to apply to these particles which are in a potential field. So remember that to accelerate a potential, if you want to accelerate an electron, you need a certain potential. Let's say you have like 50 volts. So at 50 volts, times the charge will give you your energy. So guys, you have to end here. The other stuff you're going to know from Wale. I think somebody was asking about the quizzes. You get to know them from Wale. And let me see quickly if there's something in the chat before I leave. Iceberg gives K as 1 over wavelength, 2 pi over wavelength. Is it okay to use one of them? Essentially, K is 2 pi over the wavelength. I think in that case, we're simply relating K and wavelength. We're not defining it. Iceberg himself goes on to say that to give the correct representation of K. What else? I think that's it, guys. Have a good day. We'll see you soon. Bye.